Alright guys, so in this video we're going to talk about modeling with differential equations and also solving separable differential equations. Now let's start with what a differential equation is. A differential equation is an equation with differentials in it. And that seems kind of obvious. But the question is then, what is differentials? Well, differentials are derivatives. So essentially, rather than having an equation described in terms of x's and y's, you could have an equation termed in x's, y's, or y primes and things like that. So, for example, you might have, say, what we call a second order differential equation, something like this. Y prime plus 3y prime minus 4 equals 5 or something like this. Okay? Well, this thing here is a differential equation. It has a second derivative and a first derivative. We call this a second order differential equation. But in general, what this is that we have times when we're dealing with kind of a relationship that can be described in rates of change, in this case acceleration and velocity perhaps. And that relationship is describable with these differentials. And you might think, well, that seems kind of silly because wouldn't it just be easier to describe it in terms of like x and y? And the answer to that is, I mean, yeah, sort of sometimes. There are times when it's easier to describe it in terms of x and y perhaps, but there are actually many times where it is much easier to describe a some kind of situation that's occurring in terms of its rates of change. So, basically, again, a differential equation is an equation that contains an unknown function and some of its derivatives, known as differentials. Okay? It is incredibly common because, as mentioned, in real-world situations, it's normal to use like changes to predict future behavior. That's pretty normal. And in fact, I think a good example of this is in something nice and simple, which is a falling object. Suppose we drop a ball from the top of a building. What do we know about the motion of this object? Well, what we know is we do not know, for example, distance with respect to time. We could not, from that information, we could not describe our distance with respect to time. So that is, where is it at any given point? And you might say, well, that's pretty normal. I would expect not to be able to describe everything based on such little information. But the reality is we can describe this eventually if we start with rates of change. So if a ball is dropped, the only rate of change that's occurring on it is its acceleration. We're going to start with its acceleration, and the acceleration of this is due to gravity. So if we talk about this as like a of t, the acceleration, well, the acceleration is negative 9.8 meters per second squared. Now, this right here is an equation using a rate of change. It's y double prime is equal to something. Now, that's just the second derivative, but it's still technically a differential equation. It's an equation with a differential in it. Now, we are now going to describe this thing in terms of velocity. So if we integrate this thing, we know that the velocity with respect to time then is the integral of acceleration, which would be negative 9.8 meters per second squared times t seconds, if you think about it, because we're integrating this. This is just a constant, right? And so what we end up with, plus some c. Okay, so what we really end up with is these seconds cancel, one of them at least, and we get v of t is equal to negative 9.8 meters per second. That's a velocity, that makes sense, t. So really I should put this first. Negative 9.8 t meters per second plus some constant. Now if we think about it, what is this constant? Well, it's a constant describing a constant meter per second, which is the velocity, that is our initial velocity, our v sub naught. So we could really call this c v sub naught, initial velocity. Okay, now in our case, initial velocity is 0, but let's just stick with this as a general sense. This would be if we had a ball and we threw it not just dropped it, it also includes if we were to like throw it or something, potentially. Okay. So again, our v sub naught is 0, but we'll continue on with this. So now we have our velocity, and we can find our distance with respect to time by taking the integral of this thing. So distance with respect to time is equal to negative 9.8 t squared over 2. Now, we put another t in here, which is seconds, so this meters per second becomes meters, plus v sub naught t plus some new constant. Now, if we think about this, again, we're in meters, so this c is describing the meters, some constant meters, which in our case is our starting position, our initial displacement. So how high up we drop the ball from, perhaps. So that is to say our distance with respect to time is equal to this negative 9.8 over 2 t squared plus v sub naught t plus like initial displacement. Maybe we'll call it like d sub naught or something. Okay, so now from here we basically can describe, so from one rate of change we're able to describe the distance with respect to time. We're able to describe our velocity. We can describe all kinds of things based on one rate of change. And so what's important here to note is that rates of change are actually often much easier to measure than kind of what we would consider the more simplified function, the distance with respect to time. And again, for our distance with respect to time, this would just be d of t is equal to negative 9.8 over 2 t squared. V sub naught is the initial velocity, which is 0, and d sub naught is our like displacement. So maybe the building is 100 feet tall or something like that, so or 100 meters tall, so we have 100. Now this would obviously hold up as long as the object doesn't hit terminal velocity, but anyway. So again, the point here is that we often are dealing with rates of change because they're easier to measure, and so you need to be able to solve then, a problem that involves rates of change, because that's really common in the real world. So consider the following. Suppose we're driving a car and we know that dm dt is 55, where m is distance traveled in miles and t is time in hours. What does this describe? Well, again, this is miles over hours, so that would be miles per hour. So basically, we are describing that our car is driving 55 miles per hour. Okay. So what's this graph look like? Well, this is a constant velocity. So our velocity with respect to time, so kind of like if we call this v of t and this is t, then it's just a constant at 55. Okay. So now what does the integral from 0 to 10 of dm dt mean? Well, what this means is we are taking the total distance that is being traveled over those 10 hours. So driving for 10 hours, we're taking the integral from 0 to 10, and that will give us the total distance traveled in that time. Now, what is m of t? Well, again, this dm dt, this thing is 55. If we were to integrate this thing, so what we're going to do is we're going to integrate this by moving this dt over. We'd have dm is equal to 55 dt, and we'd integrate it on both sides. The integral of functionally 1 dm would be m. The integral of 55 dt would be 55t plus some c. So essentially what we have is the miles is equal to 55 times our time plus some constant. That is, in this case, our constant is how far we had already traveled at the start of time. If we want to set it at the origin of 0, then it would just be 0, but otherwise we'd have to tell it. So again, this is another situation in which we are describing something in terms of a rate of change, but we're able to describe more things off of that rate of change. And one of the things that we've just done here is something we're going to talk about in a little bit is solving this as a separable differential equation. Notice we separated these dm and dt and then integrated both sides. We're going to come back to that. Now, a classic example of differential equations is a model for growth of a population. So this assumes that population grows at a rate proportional to the size of the population, which is reasonable under ideal conditions such as unlimited environment, adequate nutrition, absence of predators, immunity from disease and stuff. So we can get more advanced population models, but at least for an initial point, we can often follow a population model with these assumptions, at least until a certain point. So for example, basically, what we like to think about is if t is time, the independent variable, and p is the size of the population, that is the dependent variable, p with respect to t, then the rate of growth of a population is a first-order differential equation. The derivative of p with respect to t is k times p, where k is a proportionality constant. Obviously, our population must be more than 0, so if k is positive, the population will grow, and if it's negative, then it shrinks. But what would a function p look like? Well, essentially, we have this function of p that's dependent on, like this rate of change of our population with respect to time is dependent on p, like our current population. So the more population we have, then perhaps we're going to grow more or less depending on the situation. So our function p, well, if we solve this thing, again, we have d of p over d of t is equal to kp. Okay. Well, if we move this t over and we get dp is equal to kp dt, okay, those letters all sound way too similar. Well, if we were to integrate this, the problem is we have a p here. And we don't actually want a p here because we're integrating with respect to dt here. So we want it over here. So how do we do that? We divide by p to move it over. And we get 1 over p dp is equal to k dt. And now we integrate this thing with respect to their variables here. K is a constant, so it's just a constant. The integral of 1 over p dp is going to be natural log of p, our population, which is equal to our kt plus c, some other constant. This is our proportionality constant. This is our constant of integration. Now, if we want to know, first of all, population's positive, so we don't need this absolute value. We have natural log of p is equal to proportionality constant times t plus c. All right, well, how do we solve for p? Well, we take e to the power. And so this would cancel, and we get p is equal to e to the kt plus c, which is, if we think about this, this is like saying p, which is equal to e to the kt times e to the c, because when we have two things same base and we multiply them, we add their exponents. Now, e to the c, a constant to another constant, is itself just a constant. And so what we end up with is p equals c e to the kt, where c here is the initial amount. P is the population after some time. We could call it P of t. C is the initial population. Maybe we'll call this P sub naught or something like that. E to the kt, where k is the rate of change, like the percent growth of the population or decay. This right here, what this is describing is continuous compound interest, basically. That is A equals PE to the RT, where R or K, that's our rate of change. T is time. P is our initial amount, P sub naught here. A is our amount after some time. So that's what that is describing. And again, this is just a first order differential equation that we're describing here. All right, so we have these things, they're called family of solutions. Basically, without some initial value, such as the initial population in this case, we can't actually solve a differential equation in what we call explicit terms. That is, we'll have some c. So in this previous one, we had like p of t is equal to p sub naught or some c, some constant. We don't really know what that constant is other than we know it's the initial population. But without any more information, we can't really find it out exactly. And so we have these things that are called families of solutions, where basically, depending on what our initial value is, we start to follow these different curves. And these things can be shown with something what we call slope fields or direction fields, which when you're in DiffEQ, you'll see those a lot more. And to be honest, I don't really get super excited about them, but it's very clear that people in differential equations get super excited about slope fields. We'll show you that. I'll show you that at some point. In fact, I can't follow that link. Let me just pull it up. I can follow it on a PowerPoint, so I'll follow the link elsewhere. Okay. So basically, we have some function here, and this is what slope fields look like. Essentially, depending on where we start, it then follows these curves. So like if we started here, then it would go into this and then follow this line for a bit or whatever. And so it tends to just follow these curves. You can kind of see where these slopes are moving. And basically what it means is, depending on where you start, like if I start, say, somewhere here, then I'm going to follow this kind of curve here. If I start here, then I'm just going to follow here. If I start close to the axes here, I'm pretty much going to stick next to it. So again, it's just kind of dependent on our constants. And if we follow this page here, you can mess around with all kinds of different differential equations. dy dt is equal to something. And we can get a bunch of different directional fields or slope fields from it. Okay. But again, it all just depends on what your initial amount is. So, you know, if we have an initial amount starting perhaps here, then we're going to follow this red line. If we start here, we're following this. If we start down here, it's decreasing, etc. All right, so let's now talk about one of the most basic aspects of solving differential equations, and that is verifying whether a function y equals ln of x is a solution to this differential equation. So we have this differential equation, x y double prime minus y prime equals 0. This is what we call a second order differential equation. And so this is the second derivative and this is the first derivative. And so what we're saying is, if we take x and we multiply it by some function's second derivative, and then subtract the first derivative, we get 0. And we want to see, is this actually true? Well, if we think we have a function that might be the case, y equals ln x, all we have to do is plug it into here. It's not actually asking for y, but we can do a y prime. Y prime would be the derivative of ln x, which is 1 over x. And then y double prime would be, this is like saying x to the negative 1. So y double prime then is going to be negative 1 times x to the negative 2, which is to say negative 1 over x squared. So we'll see if this actually ends up being true. We have a y double prime, we have a y prime. We'll plug these into this thing, and we get x times y double prime, 1 over x squared, and it's a negative, minus 1 over x is equal to 0. So let's see if this is the case. Well, x times negative here, that would be a negative 1 over x, minus 1 over x, which is negative 2 over x, which is not 0. So this isn't true. However, if perhaps we had a differential equation that was like xy double prime plus y prime equals 0, something like this, then this could be true. So essentially what we're doing is we go, all right, well, plugging these things in, x times y double prime, which is negative 1 over x squared, plus 1 over x. Okay. This would be 0, so this would solve that differential equation if this was our differential equation. So again, this is negative 1 over x plus 1 over x, which is 0. So it isn't here, but if we change this from a minus to a plus, it would be. So essentially, this doesn't solve this differential equation, but it does solve this one. Now, when you take differential equations, you will basically spend the entire class learning different methods of solving differential equations because essentially they are more complicated integration as far as their equations with integrals in them. And so essentially what happens is that much like integration, there isn't one rule to solve everything unless you're an engineer and then all they do is run kutta. But it's an approximation method. But as far as finding exact, there is no one way to solve everything basically, or at least not a great way to solve everything. And so we learn a bunch of methods of families of solutions where we go, okay, well, this is this particular type of differential equation. We're going to use this method to solve it, much like our integration, where we go, okay, well, this is a U sub, this is an integration by parts, this is a inverse trig substitution, etc. Okay, so let's do another problem with population. Suppose we reintroduce 12 wolves into a local area, and we can describe the change in the population of wolves as dw dt is equal to 0.2w, where w is the number of wolves and t is the number of years since their reintroduction. What is the rate of change when we have 50 wolves? And also, how many wolves do we expect to have in 10 years? Okay. So let's start with the first question. What's the rate of change when we have 50 wolves? Well, that is dw dt is the change in wolves per year at any given time. So that is our rate of change. So that is our wolf with respect to time, our change in wolves. So maybe like birth with respect to time or something like that. Okay. So that is the wolves per year that are increasing. So it's 0.2 times 50. All right, so going to Desmos, 0.2 times 50 is 10. So what that is describing is 10 wolves per year in growth. So essentially, 10 new wolves are being born each year when we have 50 wolves. So again, it's dependent on how many wolves there are. So how many wolves do we expect to have in 10 years? Well, essentially, this is our rate of change, and we know that we basically have a rate of change that's changing depending on how many wolves we have at different times. So we're increasing by 10 when we have 50, but what about when we have 12 at the start? Well, we could obviously plug in 12 and find that, and then work our way through the years. But that's actually kind of complicated. Instead, what we're going to do is we're going to integrate this thing. We have dw dt is equal to 0.2w, and what we want to do is we want to get our w's to one side and our dt's to the other side. So we have this thing, this w here, and we want to multiply it, because think about when we integrate things, it's always some like x squared dx, where dx is being multiplied. It's never like plus dx or something like that. So we don't want to subtract this 0.2 over. We want to divide a w. So I'm going to take this and divide both sides by w. Okay. And we get 1 over w dw dt is equal to 0.2. Now I want to get this dt away, so I'm going to multiply both sides by dt, and I get 1 over w dw is equal to 0.2 dt. Now what this here is now is we have a dw and a dt, so if we integrate both sides, this one's with respect to w, this with respect to t, we get ln w. Now w here, it's wolves, it's a positive only, so I don't have to have the absolute value, is equal to 0.2t plus c. Now what is this describing then? This is the natural log of wolves is equal to 0.2t plus c, where c is some constant, and in our case it's the, well, we'll deal with that once we actually can get w by itself. So let's start with that. So first off, we need to get w by itself. That is to say, we are going to take e to the power on both sides. That will cancel, and we get w equals e to the 0.2t plus c, much like we've seen in another problem. Now, same thing as before. This plus, we can just write this as e of 0.2t times e to the c. And because, again, plus is multiplication of the same base here, okay? We can rewrite a constant to a constant as some other constant. So wolves equal, like, we'll call it p sub naught e to the 0.2t, because that's what this c is, this initial population. So the number of wolves is equal to our initial wolves times e to the 0.2t. That is how we can describe our population of wolves. Now, in our problem, our initial wolf population was 12. So that is, the wolf population with respect to time is 12 times e to the 0.2t. So this 0.2 is telling me that the population is increasing by 20% a year, which is pretty significant. So if I want to know what is how many wolves do we expect to have in 10 years, we have our wolf population in terms of t. So wolf in our 20 years, I believe it was 10 years. Good thing I checked. 10 years is equal to 12 e to the 0.2 times 10. So if we take a look at that, we end up with 12 times e to the 0.2 times 10. And we have 88.6 wolves, which sounds like 88 wolves. We don't have 89 wolves yet. I mean, we could round up if we wanted, but we would have 88 wolves. So again, this is just continuous compound interest in this case. We have some exponential here. Okay. So technically speaking, one could say that, well, if it's continuous compound interest, it's not actually increasing by 20% per year. It's actually increasing by a bit more than 20% because continuous compound interest actually grows at a higher annual percent yield than the number implies. But whatever, about 20%. Okay, so we'd have 88 wolves in 10 years is the point of this. All right, so what have we done? Well, basically, we've been talking about separable equations. That is one of the most basic methods of solving differential equations. Basically, if we can separate the equation into y, like say one variable on one side with like d that variable, and then all the other variables to the other side with d of the other variable, then we can solve it by just integrating both sides according to those variables. This is one of many different methods of solving differential equations, and like I said, it's the most basic. So let's see an example of this. Find the solution to the differential equation that satisfies the given initial condition. dy over dx is equal to x e to the y. Okay, well, basically what we want to do is we want to get our y's to one side and our x's to the other with that dx. So keeping in mind that we want to be multiplying or dividing them so that they're being multiplied by the dy or dx, not being plus or minus. So first thing, I'm going to multiply the dx over. So I have dy is equal to x e to the y dx. Now, another thing I should note here is that we have an initial value, y of 0 is 0. This is called the initial condition, and we sometimes refer to these as initial value problems. Basically, we know some differential equation, and we know of an initial value. So that is, if we were talking maybe in time of t, like the value when time is 0 in this case, perhaps, or whatever, okay? So that's just something to be aware of. We can, with an initial value, we can solve this differential equation. If it's a second order differential equation, like in the case of our falling object here, we actually need two initial values. In this case, this was the initial velocity and the initial distance off the ground to be able to just solve it explicitly. And obviously a third order differential equation, which means a third derivative, would require three initial values to be able to find it explicitly. Okay. Anyway, let's get back to this. We have dx here, and x is on that side too. That's good, but now we need to get that y over. So what we need to do is divide both sides by e to the y. And we get e to the, so 1 over e to the y dy is equal to x dx. So that is to say, we have e to the negative y dy is equal to x dx. All right, so now what we need to do is we need to integrate this. We have separated them. We're going to integrate both sides. The integral of e to the negative y is going to be e to the negative y times negative 1, which is equal to x squared plus some c. All right, so now we have e to the negative y times the negative 1 is equal to x squared plus some c. Now, if you notice, we have some negative values, so obviously the c has to be some sort of negative for this to be able to work, and we can actually see that. We'll find what that c is. We're going to plug in y equals 0, y of 0 is 0. So that is to say when x is 0, y is also 0. So we can plug that in at this stage if we want. So negative e to the 0 is equal to 0 squared plus c. So e to the 0 is 1. This is negative 1 is equal to our constant here, c. So what we have then is negative e to the negative y is equal to x squared minus 1. This is explicit, sort of, but we need to actually solve for y here. So what we're going to do is we're going to multiply or divide everything by negative 1. So we get e to the negative y is equal to negative x squared plus 1. And now what we need to do is natural log both sides. This will enable us to bring our exponent down. We have negative y is equal to natural log of negative x squared plus 1. And if we now divide by a negative or multiply, we get y equals negative natural log negative x squared plus 1. All right, so this right here is our equation y. So we have now solved for y, and it is y equals negative natural log of negative x squared plus 1. So obviously our domain here, if we think about this thing, negative x squared plus 1 has to be greater than 0. So that is to say 1 has to be greater than x squared. That is to say x has to be less than 1, x squared has to be less than 1, something like that. Okay, so if we take the square root of this, we'd have x is less than 1, but also has to be greater than negative 1. So x is somewhere in this range, but it is worth noting that. But here we have it. All right, let's see another one. Find the solution to the differential equation that satisfies the given initial condition. Okay, so we have dy dx is equal to the square root yx, where y of 1 is 2. Okay, so again, we'll be able to solve this. Now, the first thing we want to do is we have dy over dx. I'm going to split these up. So this is like saying y to the 1/2 and x to the 1/2. Now I can oh, I did dt for some reason. dx, there we go. Now we need to move the dx to one side, the y's to the other. So that means that if I'm going to divide by y to the 1/2, I have 1 over y to the 1/2 dy is equal to x to the 1/2 dx. Alrighty. So essentially, this is like saying y to the negative 1/2 dy is equal to x to the 1/2 dx, and we are going to integrate this thing here, and we have that would be y to the 1/2 divided by 1/2 is equal to x to the 3/2 over 3/2 plus c. Now you'll notice that I only put the constant of integration on one side, and I generally do it on the x side. That's just a Forza habit. We don't need it on both sides because a constant on this side and a constant on this side, if we move them to one side, would just be another constant. So we just do it on one side or the other. It doesn't really matter. And I generally just stick it onto the x side, not the y side. So we end up with, so divided by 1/2 is like saying times 2. So 2y to the 1/2 is equal to 2/3 x to the 3/2 plus c. Now at this stage, we could find y of 1 is 2 if we want. So let's go ahead and do that. So y of 1, that is when x is 1, y is 2. So we have 2 times the square root of 2 is equal to 2/3 times 1 to the 3/2 plus c. So that means that we have 2 square root 2 is equal to 2/3 plus c. So I'm going to subtract 2/3 from both sides. And we end up with 2 square root 2 minus 2 over 3 is our c. So that is to say, if we were to write this as like a 3 over 3 here, okay, we'd have 6 square root 2 minus 2 over 3. This is our c. Okay, so we have this constant here. So let's go ahead and copy this down. So we have now found our constant. Now we could also find our constant later on if we want. It doesn't really matter, but in this form it is our constant at this stage. So it kind of depends on what we want to do, whether we want to deal with it here or later. Now one of the benefits to doing it right away is obviously we can easily keep track of this thing. The other option is leaving it. There's a benefit because like if we divide everything by 2 here, then this constant would just be some new constant, but now divisible by 2. And we can still use our initial values at the end once we've solved for y, if we prefer. But I'm going to just stick with since I already solved it. We have 2y to the 1/2 is equal to 2 over 3x to the 3 over 2 plus 6 square roots 2 minus 2 over 3. Okay, so now we're going to solve for y. We're going to divide everything by 2. So we get y to the 1/2 is equal to, so 2/3 over 2 is just going to be 1/3. So we have 1/3 x to the 3/2 plus this 2 and a 2 on top here will cancel. So basically this is like saying if we factor out 2, we'd have 3 square roots 2 minus 1. So this 2 and this 2 cancels, and we have 3 square roots 2 minus 1 over 3. Okay, so we're here. Now what we need to do is square everything. And we get y equals 1/3 x to the 3 over 2 plus 3 square roots 2 minus 1 over 3 squared. And this is our function that we're talking about that would solve this differential equation. Okay, so that is our separable differential equations. So again, you'll see more of this when you get into DiffyQ, since that's all we do is solve differential equations, but this is one of those ones that is going to be very trivial compared to many of the other methods that we're going to be solving. But it just takes a bit of algebra, that's all. And that's the reality of differential equations. When you get into DiffyQ, if you are not strong in algebra, you are going to struggle. If you have solid algebra skills, it is going to be easy. You may not understand what you're doing at every given moment, but you'll at least know how to do it. For me personally, when I left it, I was like, wow, that class wasn't that hard. But man, I don't know what the heck I was doing most of the time. I was just doing math. Like I saw it, I did this thing because I knew I had to do the thing. But why did I do the thing? Because I was told to. So that's kind of one of the issues. It wasn't until I went back and taught it that it really clicked on like what I'm doing and why I'm doing it, rather than I just knew how to do it. But again, that's our differential equations. So, thanks for watching.